So welcome everybody to the second lecture in the 20th Distinguished Lecture Series of the Department of Mathematics of the University of Haifa. And I'm happy to welcome again Professor Maxim Kontsevich.
Okay, so share screen. Okay.
Oh, yes.
Okay. Yeah, so you see me?
Yes.
Okay, so I apologize for listeners of previous lecture who are familiar with Gromov fitness theory. It was very standard material last time, but today is definitely will be not. Yeah, so the plan will have kind of three parts. The first part I will describe what is maximal isomandromy deformations and some factorization gluing related to this. This will be the main body of the talk, and then I'll speak a little bit about testing ground, which is Landau-Ginzburg model, and then about semi-orthogonal decomposition for Fano varieties and beyond. Okay, so what is this maximal isomandromy deformations, their factorizations, and gluing? The terminology is probably not optimal, and there was some competing terminology, but let's stick with it. Yeah, so let's recall our story from the previous lecture about Gromov-Peter invariance on genus 0. We start with projective variety, or symplectic manifold if we want its infinity version. Let's have a complex numbers. We have a class of some ample bundle, one in projective embedding. And then we'll construct a quantum product on cohomology, which depends formally on parameters, which are coordinates on cohomology of my manifold. And the dual basis at delta I, dual to coordinates. And then there's also one variable capital T, which oops, there's some misprint here. It comes from weights for the curve. It's T to power the area of the curve. So this horizontal line is part of T. It was accidentally removed. Okay. Yeah, so we have number of coordinates is dimension of cohomology plus 1. So it's better to remove one of coordinates Ti0, which correspond to class delta 0, which is class of symplectic form in second cohomology. And now the number of parameters will be dimension of my cohomology. The tangent space at each point to this parameter space, which are still formal, is identified with my space of cohomology, and I should remove my kind of limiting point when t equal to 0. Namely, there are tangent vectors corresponding to coordinates which are not I0, and they correspond to this dual basis delta I. And for variable t, I consider logarithmic vector field t over dt as a tangent vector, and this corresponds to this delta I0. So in a sense, this capital T is exponent of small t with index I0. Okay, so we get this formal gadget.
May I ask a question?
Yeah.
So you replaced the variable ti0 with capital T.
In a sense, the kind of one is redundant. They're related, so I just remove logarithmic version and go to exponential version. Yeah. Now I have series with kind of right number of variables, and now assume that my series F0, which I will not write, is convergent for small values of variables. Yeah. In principle, can be and should be avoided, because when I want to develop general theory, I don't want to base on unproven conjecture about convergence, but then it will make things more difficult to formulate. So I will stick with this analytic situation, which in fact respond to the real life. Okay, so if I have domain of convergence, and this capital T will be strictly non-zero for me, so I have certain non-empty domain of convergence, which I denote by M, which will be analytic supermanifold of dimension equal to the dimension of my cohomology. Okay, now let's proceed the following way. So as I wrote at the end of last lecture, in a formal setting, but now we're doing an analytic setting, when I multiply my manifold M with complex line with coordinate which are denoted by u. Then we have a holomorphic supervector bundle, which is in fact was trivialized vector bundle, but let's temporarily forget it. So I get holomorphic vector bundle, and it carries a meromorphic flat connection. And its connection has pole on the hypersurface when variable u is equal to 0. So it will be a copy of my manifold M. And the property of this connection are the following. If you consider the lift of vector field u squared du, then I get differential operators without any poles. So it will be regular differential operator. So it's the same as du. If you consider lift for du, I get pole of order 2, at most 2. And similarly, if I consider any vector field in first coordinate, in first factor M, any vector field psi, and multiply by u, we get still vector field on M times C, and take a lift of this, then it has no poles at all. Yeah, so it's a similar condition. Yeah, in fact, I formulated things in the trivialization, and for me it will be a secondary structure. So, so what I have also have a trivialization. So it means that for any point on a manifold and for any complex number, I identify my fiber with some given supervector space H, which is at the end of the day cohomology of my variety when I do Gromov-Hitchens theory. And vector field du is lift of vector fields du has just two terms in u expansion. In du times u2 minus 2 some operator which depends on a point M, and u minus 1 times operator g which doesn't depend on point M, it's for some grading operator. And similarly, if I lift vector field and I introduce some local coordinates du/ti, I get du/ti plus u inverse some matrix valued function ai. Okay, yeah, and in fact, in examples with Gromov-Hitchens theory, we have even more. Our manifold M has also canonical affine structure, but I'll again forget about it. So for me, it will be just some general supermanifold. Yeah, so forget about this trivialization. So what we are doing now, we consider supermanifold, analytic supermanifold, analytic supervector bundle, and so before I was a bundle of product of manifold with whole coordinate line C, but right now I consider as a germ of C at point 0, and size kind of size of a germ depends on a point of manifold. So maybe I consider more precisely product of manifold with complex lines with C, and consider germ of a close at close subset M cross 0. Now, so I get this supervector bundle, and out with a meromorphic connection with poles at this hypersurface M cross 0, and satisfying these constraints A and B. So it's got kind of second pole in direction U, and first order pole if you consider lift of vector fields in direction M. And call it an admissible isomonomic deformation. Again, there are possibly other names. I think Klaus Hertling has some 5 or 6 different names of related structures, TERP structure, something like this. Yeah, so there's some abbreviations. Yeah, so let's stick with this name. Yeah, so it's a deformation, or if you want to see deformation of what? M is parameter space, deformation of connections of bundles on a small disk and U variable with poles of order 2. So we really treat kind of separately U coordinate and M as parameters. Yeah.
But you have a derivative with respect to M as well, yeah?
As well, yeah, yes, it's isomorphic deformation.
Does this connection relate to the potential F that you defined in the last
lecture? Yes, in the last lecture I wrote a formula, but one can consider this abstract structure, some supermanifold. You multiply by a small disk and make this some bundle on it and have this connection, flat connection.
But is F a flat section of this connection? Or?
F?
The
F?
potential.
No. F it's something. It's not. It's not directly. F it's function. It's going to be section because bundle is of higher rank. Yeah. Okay, so we get this gadget. Now, what we can do? Yeah, first of all, if you have point on my manifold M parameter space, then I get a distinguished supervector space, which is a fiber of my bundle in point X, and second coordinate U is equal to 0, called H of X. Yeah, because it's now not trivialized, it's just some holomorphic vector bundle. Then for this point, I have a canonical operator Kx, depending on X, and endomorphism of this fiber. What is Kx? I now consider connection in U variable, choose some trivialization. Then I write, it will be a series starting, if leaf vector field 0 du, I get 0 du plus series starting from U minus 2. And the leading term doesn't depend on choice of trivialization. So I get well-defined operator in this fiber at 0. Okay, and denote it by Kx. And also I get a map from the tangent space. I do not denote map at all. There's no need. To endomorphism of this fiber at 0. Namely, okay, let's do local coordinates, but it doesn't really matter. If consider a derivative with respect to some local coordinates in M, then I consider lift of this guy, gain some serialization. Oh, sorry, because when I was editing, I just accidentally remove. You get DOTI plus U inverse, and here will be bold AI. So the same bold AI is the next line. Okay, so I get for each tangent vector, I get operator, it's a linear map. And the flatness of the connection, if consider the equation for flatness just in leading terms in U, automatically implies two things. First, this operator AI commute with each other, because it was flat connection anyhow. And also the commute with operator K. So I get a lot of commuting operators. Let's first concentrate on commuting operators A. And I propose the following axiom, that this map from the tangent space to space of endomorphism is an inclusion. So we realize how tangent space is a subspace in space of endomorphism. So we get some family of commuting operators, and the axiom is form a maximal commuting family of operators. So we cannot add any more commuting operators without changing linear span. Okay, so what does it mean? It means that this subspace in endomorphism form a supercommutative associative unital algebra. When you get maximal family of operators, you have unit, it's commutative identity operators. It's closed on the, it can add products, and that's it. And then, because it's maximal, the space is also free rank 1, 0 or 0, 1, because we're in the superworld model of this algebra. Okay, so we get this commutative algebra and free rank 1 model. We do not choose any generator. And you see that also here the story has kind of two flavors, which are completely irrelevant for what I'm talking later, but still there's odd and even, because this free model could be of two types. Okay, so we call such a structure a maximal admissible Zamandromi deformation. So sometimes I mean admissible, so it's maximal Zamandromi deformation. And presumably it means that my Eisenman-Romney deformation I cannot include a non-trivial larger Eisenman-Romney deformation. I think it follows from the axiomatics, but I didn't check. Okay, so we get this structure. Now what? So we have this maximal Eisenman-Romney deformation. I claim is that we have a canonical vector field, which I denote by E, because you call it Euler vector field. What is this vector field? So you see that we have maximal commuting family of operators A, Xi, Xi are all tangent vector at some point, but operator Kx commute with them. So in principle, we can add them, but because it's maximal, it shouldn't be able to add this operator. So it means that this kx coincides is exactly one of these operators by my axiomatic. So it means that I have a specific tangent vector called E sub x, and it will be the value of my Euler vector field at point x. So I define the value of Euler vector fields at any point. So I get certain remarkable vector field. And recall that we have a product on the tangent bundle, pointwise product, because it's commutative algebra anyhow, denoted by star. And using the product, one can make new vector field, just raises to some powers, 0, 1. 0 is possible because it's unital algebra. So one can make arbitrary integer power, non-negative integer power, get e to power k, this vector field. And here's first interesting claim that if you have infinitely many vector fields, they form an action of Wheatley algebra, formal polynomial vector fields in one variable. So if we take commutator e to power k and e to power l respect to product, we will l minus k e to power k plus l minus 1. And it's completely similar to the following formula. If you take z to power k dy dz, z to power l dz, you take commutator, get l minus k, z to power k plus l minus 1 dy dz. So the kind of stupidest example will be the following of this structure. Your manifold is a line with coordinate z. The multiplication tangent space is just given by 1, and then you get Euler vector field called z dy dz, and then its power will be z to power k dy dz, and then you have this kind of basic one-dimensional example which repeats in high-dimensional situation.
Frobenius manifold structure by itself.
It's not Frobenius manifold because I didn't say that my algebra is Frobenius algebra.
Oh, no trace.
There's no scalar product. And in fact, this formalism applies to this non-compact situation about which you asked yesterday. When you get non-compact variety, there's no point-carrier duality, the same story works.
Yeah, so Maxim, could you miss something? What is the power of a vector field?
It's a power with respect to multiplication. I have multiplication as tangent bundle.
Okay.
Yeah. So that's a very remarkable structure. In fact, it has as the origin, which I didn't write here, namely, you consider Calabi-Yau category, which will be smooth and compact, if you know what is it, and with the generation of Hoche to de Rham spectral sequence. Actually, you don't need Calabi-Yau structure at all on this category. Oh, in fact, you don't need anything, sorry. You consider any A infinity or DG category. And which will be Z2 graded, not necessarily Z graded. And then we consider kind of maybe derived modular space of deformation of this category. It will be kind of analog of this M, and it carries some canonical vector field. Namely, for each Z2 graded category, you can have canonical deformation. You rescale all high multiplication by the same constant, because the equation of associativity is homogeneous of degree 2. You get some Euler vector field. The tangent bundle to the modular space of categories has a commutative product because it's a Hochschild cohomology. And then you can form powers of this Euler vector field, and the same story works. So it's very, very general situations, not in this complex analytic geometry, but in some algebraic setting as well. So you get the section of Witt algebras on infinity categories. And I don't think it's actually well documented. I don't think it's ever was ever written at all. Okay, so now let's return to our basic situation. So we get this super manifold with a bundle. Then for each point, I will define a finite set of complex numbers, which is known as a spectrum associated to this point. yeah, in principle, you can ask me, because what do you mean by point? Because there are fermionic variables, I consider just purely bosonic points. So the spectrum of X will be spectrum of this operator Kx. It's the same as by definition of multiplication by Ex. That's how I defined Ex. Yeah, so it's some finite set of complex numbers. And what I claim is my manifold M has a remarkable factorization structure. Pick any point and write spectrum as a collection of distinct numbers, Z1 up to ZL. Then I claim that a neighborhood of this point canonically split into the product. So M near X is a product of some smaller supermanifold Mi of strictly positive dimension near Xi. And because what I Xi, because when I identify manifold with a product, I can write point X as a collection of points Xi on my factors Mi. And moreover, there will be action of Wheatley algebra on each Mi, and this decomposition of the product is compatible with the action of Wheatley algebra. By the way, this Wheatley algebra can be set as a vector fields, polynomial vector field setting in the variable Z, which exactly where the spectrum lives. And now what goes on? Each factor, which is a germ of supermanifold near Xi, carries its own maximal isomandromic deformation. And in particular, you get spectra for this individual isomandromic deformations. When you consider point close to point Xi prime close to Xi, then the spectrum will be certain subset which is very close to one element subset Zi. And when you consider spectrum of this corresponding point on my big manifold, X1 prime, blah, blah, comma, XL prime, it will be exactly equal to the union of the spectrum because deform a little bit, they do not interact with each other. So what I say is that your spectrum, if you move a little point, splits a little bit, which is normally what happens with spectra of operators. If you had spectrum of some operator, deformed a little bit, spectrum splits in some small groups. But claims will be kind of will be in completely independent way, so it will be a product structure. And what I say is that it's not only product, but there are other things beyond spectra. There are these isomandromic deformations, the bundles with connections, and the claims that somehow related. So the original isomandromic structure on M, so the bundle with connection and so on, is obtained from the same structures on Mi by applying certain procedure. What is applying? It's something, but procedure depends on some locally constant gluing data.
How do you get Mi from M? Can you repeat?
Yeah, for example, I can explain this without writing any formulas like this. You consider any point near X, yeah? Then at this point, you get a spectrum, which is a collection of groups of points near Z1, Z2, and so on, yeah? Because the spectrum is a little bit deformed. Now I consider a polynomial in variable Z, which equal to 0 on all groups on all eigenvalues except one, and equal to 1 on the group of eigenvalues close to Zi. I get certain projector. So I get this polynomial, and I get corresponding, apply this polynomial to earlier vector field, I get certain endomorphism, which will be a projector. I apply this endomorphism to my tangent bundle, I get a subspace. So for each index I get a subspace. And I claim that what I get commuting foliations, which gives me a decomposition of the product, independence of the product. Yeah, so it's completely geometric. What is not obvious here that you get this isomandromic deformation structure on individual MIs, some new vector bundles of smaller dimensions and flat connections. Okay. Now, so I should a little bit discuss what is gluing data and what does it mean apply. Yeah, it's that's actually the whole science about it. So the gluing data is the notion which we introduced in our paper with Tony Pantev and Lyudmila Katsarkov on hot surgical aspects of mirror symmetry. So I'll give a kind of version of this definition. Suppose I get a collection of closed disks in a complex plane, this variable z, if you like, such that bigger disk contains strictly an interior disjoint union of all other disks. So disks from 1 to L do not touch each other and do not touch the boundary of D0. What is the gluing data associated with this situation? So I first give abstract definition. I consider a constructible sheaf of, let's say, super vector spaces on this big disk, which is locally constant on each small disk and also locally constant on the complement to this union of small disk. You can contract small disks to a point. It will be usual constructible sheaf and maybe extend T0 to the whole plane. Okay, so it's what we formulated. It was a sheaf on C on a plane R2 or C with singularities at finitely many points, but it's the same story. And the property is R gamma of this sheaf is equal to 0. So it has 0 homology, H0 and H1 vanishing. There's no H2 here. Okay, so it's kind of abstract game, but one can figure out what does it mean. It's very simple thing. But the description, to make a complete description, should make certain topological choice. To make different choice, it will be description, the same description, but in different manner. So the description depends on the choice of what's called Gabrielov path. I choose, for example, a point on boundary of D0 and connect by disjoint path to some points on the boundaries of disk D1 up to DL. And if I make such a choice, then this gluing data, it will be such a very simple data of linear algebra. It will be just a collection of super vector space V1, VL, and a collection of operators for between any ordered pair. And only one axiom that operators the same index TII from VI to itself are invertible. Yeah, so it's a presentation of some kind of very stupid quiver, kind of complete graph with conditions that any loop is invertible.
But it depends only on your differential equation, yeah. So
What?
This data, it's sort of a quotient of perverse sheaves by local systems. So it's on the drum side.
Yeah, I don't. No. It's yeah.
No,
it's one can think about drum size, but I prefer not. Yeah, just it's.
But it doesn't depend on the geometry, on whatever, on category.
It's very topological. Yeah, I don't know. It just disks. That's it. Yeah. When you make different choice of Gabrielov path, you can have action of braid group, or also maybe rotation of extra point, and it will be certain action of braid group on this by automorphism of this algebra. Yeah, which is essentially kind of like path algebra occur with some invertibility. Okay, so yeah, that's some abelian category, if you like, whatever. And when you have this gluing data, it gives a collection of local systems on all possible circles of boundary of big disks and boundary of small disks. And the description is the following. So I have two languages, abstract definition and concrete description. I'll give the answer in both languages. So the local system for the big disk is the restriction of my constructible sheaf on the boundary of big disk, which should be local system because it's locally constant there. And in concrete way, it's a vector space which will be direct sum of spaces from V1 to Vn. And what will be automorphism of this guy? It will be product of three operators. One will block low diagonal, another will block diagonal, and the third one will block upper diagonal. So in the middle term, we put T11, T22 on diagonal. It's an invertible operator. For low diagonals, we put something like T21 and so on. This low diagonal part. Because of choice of Gabriel passes, I ordered my mark points in certain way, so it's really well defined. And similar for the upper triangle part, I put this Tij for I less than j.
Can you say again, why do you need to choose Gabriel passes and not just
Gabrielov, yeah.
Gabrielov passes? Why not just passes between the centers of the disks, something like that?
Yeah, no, it's a bit long story. I just want to make it short. Yeah, I give the answer. Yeah, in principle, if you want to understand how one thing is related to another, we should read our paper with Ludmila, and it's defined. It's explained.
But it's equivalent.
It's just all equivalent. Yeah, it's nothing else. Okay. Just I want to say now what is now we can consider small disks. What will be local system associated to the small disk? The fiber, the local system on, in kind of abstract language, when I get constructible sheaf, what I do, I consider a point running very close to the outer boundary of the small disk. So it runs through a bit larger circle. And now I consider sections of my sheaf restricted to a little neighborhood of my small disk relative to this running point, and consider global sections. It will be a certain space which depends on a point and which runs through a circle, get local system on circle, and an abstract in concrete description, it's a very simple one, just my space Vi with operator Tii again. So I see the little misprint here. Okay, that's the story. So now this gluing data associated to this picture disk and in some collection of smaller subdisks looks like kind of a point in a space of a little disk operand. And then one can compose gluing data. So similar to a little disk operand. Suppose I have some big disk with kind of blue boundary. It contains some collection of green disks, which contains, and each of them contains some red disks. Then if I have a gluing data for this big pair, blue disk and correction of green disks, then I get a local system of some big rank on the outer disk, and which will be equal to sum of rank of local system smaller disks. Now I can put the same things in a green disk, have some collection of red guys. Again, rank of each local system on small disks will be small from rank of delta j. So you see that rank of big guys is again equal to rank of all red guys. And the claim, if I have some gluing data for ambient space and some gluing data for small disk, I have again some gluing data on pair blue and a lot of red, and all these boundary local systems are what I have a priori. Yeah, one can maybe formulate some kind of like category to category. I don't worry about it. Okay. So what does it mean applying gluing data? Yeah, so it's
sorry to interrupt. There's a question from David Giotto.
Yeah, Gaiotto.
Just to make sure I understand, for the big circle, there is an irregular singularity of rank 1.
Yeah,
for the small circles, irregular singularity.
Yeah, no, it's a bit complicated if you think about irregular singularity. I just think about linear algebra data.
Okay.
Yeah, it's really a bit long story to. I don't really have time.
Okay.
Yeah, yeah. So what does it mean applying gluing data? Now what is going on? I say that I have some maximal deformations for some running point, maximal and then have gluing data, get maximal deformation for this union. Yeah, but in these things I speak about some families of connections in CU, and in fact this gluing works just for individual connections without any parameters, and the same things works with parameters when you need it. Yeah, so it's some kind of abstract story. If you get a connection with second order pole, just individual connection, and suppose you put consider all possible connections second order pole, and you put the following constraint: the spectrum of operator k, which is only one here, is subsets of the union of the small disk di. Then I claim that this object, or mathematical says has this notion of isomorphism, says groupoid, is the same as some kind of fiber product, some notions with some compatibility. You get connections just for each disk. You get a connection of smaller rank, such as second order pole spectrum containing this di. This connection define the local systems, because if you get connection, you can just restrict to a little disk, you get some connection. It will be, in fact, you do local system in variable u, and here it's variable z, but it turns out it's the same connection. And then this local system collection of local system S1I, you extend to this by gluing data, so you just add new extra operator Tij for I non-equal to j at the end of the day. So this adding gluing data, just adding operators Tij for I non-equal to j, because monodromy we already fixed, and make a fiber product. We get this groupoid, and it makes the local. And if we want to read what is the local system of this big disk, it will be part coming from this gluing data business. Now, so this is a version of Stokes data for connections irregular singularities. The story is roughly the following: when we get the second order pole, it's on a vector bundle which extended to 0. Now we can replace by meromorphic bundle, so we allow to divide by power of u. And then for meromorphic connections, one have Stokes data, and eventually it gives us gluing. But now the question, there was this extension of my bundle to u equal to 0. And turns out this extension to u equal to 0 will be completely separated to different pieces, and one can make this product structure. Yeah, so it's very, very non-trivial fact. In fact, all this thing looks neat, but it's pretty non-trivial. Okay, so we see that, so what's the conclusion? We see that genus 0 Gromov-Witten invariance gives a maximal admissible monodromy deformation. And this factorization structure, it's completely universal game, not related to Gromov-Witten invariance. Just for this maximal deformations, we automatically have it. But there was something which I said that let's forget about it. It was trivialization of vector bundle. And in fact, a fine structure on my manifold M as well. Where it comes from? It's come from some locally constant choice, which we call framing. It's again, it's an our paper with Milantoni. It's a locally constant filtration on my bundle when I remove 0, when I get actual flat connection, and also covariantly constant vector in the associated graded local system. In fact, it's in real life it's in a certain degree, and it satisfies certain open non-degeneracy condition. What is non-degeneracy condition? It is the following: if we extend my bundle to CP1, adding u equal to infinity, and how we extend it? Because we have local system in u direction, and to extend local system after linear, we know the same to have a locally constant filtration. It will describe the order of growth. Then the resulting bundle so the condition that there is a bundle on each kind of horizontal line is holomorphically trivial. Okay, so you see we trivialize bundle. We can trivialize bundle only in u direction, but this connection which you have in the direction of m also expand to points at infinity, and so we have also kind of at least locally get trivialization at fiber to infinity. And now we can combine it together, you get trivialization infinity, you get trivialization everywhere. Okay, so now my bundles, it's trivialized, maybe in some domain in M and to the whole product of CP1 in U direction. Now, my vector, which was, I can also, an associated gradient. Associated gradient is things which sits at infinity. It's a fiber to infinity. It's well known. And then it gives you, because trivialization gives a vector in fiber to U at 0. And we want the Bowen condition that will be cyclic vector with, for the action of my algebra on this module, rank 1 module. This vector could be even or not. Yeah, so that's it's certain choices. It depends on finitely many parameters. You choose this filtration and a vector. But in fact, in practice, there's really no even continuous parameter. It's kind of a discrete choice. Because what goes on in practice, this local system has certain Z structure, which I don't want to talk about at all. And then we call it kind of non-commutative Hodge structure because it has something like this connection along QV, it's analog of Hodge filtration. And this will be an analog of a lattice. And both this locally constant flag and this vector and associated gradient are integral with respect to complex structure. So that's in real life, you just kind of should understand and make choice in integer numbers. Okay, now I'll go to some little. Just a second, I have to remove some stupid file. Testing ground, which is Landau-Ginzburg model, which is already many things which I don't understand here. Yeah, so we'll start with the following situation. We have a possibly non-compact Kähler manifold. Why? It's not necessarily algebraic, it should be some maybe domain. And such that there exists a holomorphic volume element on it. The choice of holomorphic volume element, it's not a part of the structure, I need only existence. And I have a holomorphic map to C, which is just holomorphic function. So I get this triple or maybe double Y and W, and existing holomorphic structure is a property, not part of the structure. Now I make the following assumption. That this set of critical points of my potential, points where derivative is 0, is compact and connected and non-empty. Yeah, so this special case when it's just one point. In real life, you need only a neighborhood of this arbitrary small neighborhood of this critical locus. So we get isolated singularity, what people call it, isolated singularity, isolated critical point of a function. And what I'll construct, it will be in this most classical case, it's universal unfolding of isolated singularity has a dimension equal to the Milnor number to get a germ of manifold. What here goes on? I have a DG algebra, which is of the following form. I consider like C infinity sections of the following bundle. Consider polyvector fields in holomorphic direction, forms in anti-holomorphic direction, and bracket usual Ninhorst bracket and cup product, and with differential is d bar, and sorry, I have to write it's commutator with W. It's not, it's under some duality, it's not working. It's commutator with W, so it's misprint here. And now it's infinite dimensional algebra. I consider kind of infinite dimensional manifold of solution of Maurer-Cartan equation, d gamma plus half of gamma gamma equal to 0. Yeah, here's some kind of really kind of Banach, infinite dimensional Banach space, and modeled out by kind of local gauge equivalence. One should add some words here. Maybe consider solution in a small neighborhood of my W, some compact, small compact neighborhood, no doubt. Then the claim, I can make a quotient which will be analytic germ, not formal germ, of a supermanifold, and will carry maximal isomononormal deformation in this sense. Yeah, it's a pretty non-trivial statement. I have to write all details. Fiber of the local system, when I make u equal to 0, it will be R gamma of critical locus with a sheaf of vanishing cycle of a constant local system. Yeah. So you see that automatically has an integral lattice because I can put two integer coefficients. Yeah, so it's a nice super manifold. We understand it very well for isolated singularities. And in general, there is a part which kind of I understand pretty well what is going on here. When I consider actual deformation, maybe a small neighborhood of my critical locus as complex manifold with holomorphic function. But there are other deformations which are completely mysterious. And what is the meaning of critical values? It's still not clear to me. So it will be definitely will be not a complex manifold. It will be something else. So now I go to this third topic, which is semi-orthogonal decomposition for Fano varieties and beyond. By the way, just I want to say that in all known examples, this what's called maximal isomononormal deformation coming from Gromov-Witten invariants also comes from some Landau-Ginzburg model. So maybe Landau-Ginzburg model is really more universal source of such examples. And this Landau-Ginzburg model also fits to categorical framework because when you get this situation, when consider category of matrix factorizations, it's the property that have volume elements implies it's Calabi-Yau category, and then this general formalism for categorical world should apply and should get on formal level the same story. What I claim that in algebraic situation, when you consider general like infinity categories, you have some Lie algebra like homological Hochschild complex. You get only formal modulus space. You don't never get analytic modulus space a priori. Yeah, so it's in order to get analytic, it's some kind of extra analytic property here of my maybe non-commutative space. Okay, so now I'll return to Fano varieties. So recall Fano varieties are varieties with a positive first chain class, ample bundle, and for many, maybe all, it's hard to say till now. There exists at least one Landau-Ginzburg dual, and it's actually more special. In this case, W is a proper map. In fact, Y is algebraic, and fibers are compact. And relations are with my original variety are of two types. So first, as I told you, this isomononormal deformation coming from Gromov-Witten invariance for X is those from this Landau-Ginzburg model. So the parameters of Landau-Ginzburg model are exactly this coordinates on this whatever Frobenius manifold for X, but also derived category of coherent shifts on X is what's called Foucault-Seidel category of Y with respect to certain symplectic form and maybe B field, which depends on the complex structure on X. Yeah, that's kind of like more weak point of the whole story. I will talk in a few minutes what is Foucault-Seidel category. Yeah, so there are two relations. Just to keep in mind what is going on, if X is a toric variety, then it's well known after Butterev that it's described by something called reflexive polytope, some integer convex polytope, such as dual also integer polytope. And the dual variety is a certain non-compact toric variety with dual lattice. And the potential is sum of monomials corresponding to vertices of this reflexive polytope. This reflexive polytope has only one interior point, which is 0. Shift potential. Yeah, when I consider Gromov-Witten invariance, this for Fano varieties, this absolutely canonical kind of God-given point. And this manifold, when you put all small t variables equal to 0 and this capital T is equal to 1, which will be exponent of missing 0. So it means that you just count the cycle which you use for multiplication in just a collection of points which lies on stable cursor degree 0, or 1, 2, or whatever your cohomology classes. Just take all of them with weight 1. And then you get something absolutely remarkable potential, or at least if you don't know whether this mirror exists or not unique, at least you get some D module. If you have a concrete Landau-Gisborne model, it will be R gamma of D module of Y. It's algebraic. You take exponent of W divided by U, you get D module. Depending on parameter U, take integration over U, you get some D module of a fine line, which will have this irregular singularity second order pole, and it's a canonical extends to 0. Yeah, so you get this D module, but it's even by some integer coefficients and has very kind of unique arithmetic properties, which I don't want to talk. It's kind of very, very special differential equations, which you can study on its own. And there was a program by Vasily Golshov and Alessio Corti. They look for these equations like of order 3, 4, and so on. When you get a motivic variation of hot structure after making Fourier transforms such like this, there are very few of them. For example, in the first, it depends on some discrete parameters you put in, feed in your equation, like rank of the bundle. And first you get something like 14 different remarkable equations, then you get 94 and so on, maybe then you get thousands. And all fits perfectly well with classification of families of low dimensional Fano varieties. Like, for example, with cohomology like P3 or P4 or something like this. Yeah, so it's this absolutely remarkable coincidence between purely arithmetic equations, kind of very rigid objects, and families of Fano, because we don't have distinguished Fano. They have some certain their own parameters. Okay. Now, let's speak a little bit about Foucault-Seidel category. So Foucault-Seidel category, it depends on my variety, maybe with proper map now, W, and with choice of symplectic form. And objects of this category are roughly closed non-compact Lagrangian submanifolds in Y, such as its projection sits in a union of some disk, sufficient large disk which contains all critical values of my potential, and a ray which goes to minus infinity. Now, if we choose Gabrielov path, so we have now smaller disk sitting in big disk and with some path and drawing in minus infinity. So let's make this choice. Then we have just before going on, reading wrong order. What are home spaces in this Foucault-Seidel category? Yeah, it's something which was kind of discovered a long time ago, and it was all the stories about 93, 94. When you have these Lagrangians, which project to some kind of domain and the path, you just you're interested in home space, you just bend a little bit path. If you consider like home from blue one to red one, you bend in the blue one a little bit in the clockwise direction, and you see if this blue thing sits below the red guy, you get zero intersection, so you get no homes if things sits in the right way. And then it implies the following: this Foucault-Seidel category contains the full subcategories. If I choose this Gabrielov path, object which projects to the smaller disk and smaller path to minus infinity, and this form a semi-orthogonal decomposition. So Paul Seidel wrote a whole book about this thing. So this Foucault's ideal category is a semi-orthogonal decomposition. He wrote a book in a case when this critical values are Morse critical points, but it's very general. So it's a semi-orthogonal decomposition of collection of this S1, SL, and Holmes, what does semi-orthogonal, that any object is extension of obtained by extension, and there's no Holmes, for example, for the larger one to the smaller one. L will be number of critical values. Yeah, remarkably, this is a notion which was originally studied in Moscow School of Non-Algebraic Geometry, starting from this work by Rudakov or Gradentsev, and discussed a lot of semi-orthogonal decomposition for CP2. And then Bondel and Kapranov introduced a general definition. Then Sasha Kuznetsov is a great master of it. But the basic example is come from early work by Sasha Belinson, which has completely different origins. Namely, your X is your variety, Fano variety is projective space. And when considered derived category of coherent shifts, it has a very simple semi-orthogonal decompositions, namely consisting of shift O, O1, and up to O-pen. There's no home from O1 to O and so on. It's semi-orthogonal decomposition. And endomorphism of this direct sum will be certain finite dimensional algebra, which is derived equivalent to projective space. But now how in the center of Foucault's category, for the projective space, the potential is very simple, and critical values are roots of 1. And we get Foucault's ideal category, and we connect these things with the right way to minus infinity. You get this semi-orthogonal decomposition. Okay. And now there's also, again, a general conjecture, which is Sergei Barannikov, we worked out a long time ago. And then Boris Dubrovin independently came to this in a bit different form. So the conjecture is the following. Let's consider Fano variety and a point in this Frobenius manifold corresponding to a class in second cohomology. In mirror set, when consider Logisberg models, it corresponds to actual varieties with a function. There are other things which are not varieties of functions. There are some polyvector fields. And at the moment, I don't say anything about it. I also consider something like classical part of tame part of this whole story. And we choose a collection of Gabrielov paths. Then the conjecture will get a canonically semi-orthogonal decomposition of derived category of coherent shifts. Yeah, it's just imitated from this picture with Landau-Giesecke models that Foucault's ideal category equivalent and so on. Okay, so it's nice. Yeah, in fact, this absolute point when I put all coordinates equal to 0, it's not sufficient. If you take like P1 cross P1, you get four critical values, but 2 of them accidentally coincide. You should move a little bit. You should deform by second cohomology to separate eigenvalues which accidentally coincide. But in fact, it's not sufficient. If one make even Grassmannians, that's not enough to move along second cohomology if you want to make finer semi-orthogonal decompositions. So it looks that one should move beyond this H2 locus. And now I'll make a absolutely crazy conjecture for which I have no solid evidence. It's maybe very optimistic, and if it's true, it will be absolutely fantastic conjectures. And have no idea how to approach it. And I formulate in very, very general universality. So take any non-algebraically, or maybe algebraically closed field K, maybe in positive characteristic. Take any projective variety of this field, smooth projective variety. Now, kind of have to base on convergence, but these things can be formulated without assuming convergence, but let's do it. We have this Frobenius manifold. It's again some story how to do this variety of finite field. You don't have cohomology zero coefficients, but there's a way to do it. Anyhow, it's all difficulties are doable. Take any point on my Frobenius manifolds whose coordinates are, there's no fermionic part here, and coordinates correspond to some linear combination of cohomology classes. I choose linear combinations only of algebraic classes, and even algebraic classes defined on my base field K. And also this, then it has the eigenvalues which are complex numbers because I have complex linear combination. Then choose my Gabrielov path. Then the conjecture says that I have absolutely canonical semi-orthogonal decomposition of my derived category over my base field. Yeah, so it's really arithmetic aspects are important here, because sometimes the semi-orthogonal components decomposition, if you make extensions, will be finer, not finer. Yeah, so it's big conjecture which I want to make. I have no idea how to approach it, and that's it. Thank you.
Okay, thank you very much. Any questions?
Yeah, a couple of questions in the reverse order. So your last conjecture, it's kind of independent on the mirror symmetry. So
Absolutely, yeah. I don't formulate any mirror symmetry. I have
yeah,
regular
yeah.
finite field.
I mean that kind of if you work not over an arbitrary field, you can imagine that you have a mirror dual Fukaya-Seidel, and though this semi-orthogonal decomposition should correspond to it. Yeah.
But this Fukaya-Seidel will be derived category. It will be just tautology. Yeah,
yeah. It would be tautology. But now comes a question. The question is that on the Fukaya-Seidel side, you have this perverse Schober.
Yes. Yeah.
Okay, good. So is there any kind of perverse Schober always without assuming mirror?
No. The story is that in Fukaya-Seidel category also get Fukaya categories of fibers. That might be W, which will be something.
That's a Schober.
It will be. There's no a priori. I don't see any place for some.
Okay. Yeah, I see. And the second question is actually this last part kind of it's independent on this spectrum considerations. And my question is about this structure which arises when you consider deformations with spectra belonging to some disks or whatever.
Yes. Yeah.
Good. Now, from the point of view of this little disk opera, that's natural to compactify, and you don't.
No, I don't.
Okay. Is there any meaning for compactification when eigenvalues collide?
Yeah, no, the whole structure, I said this has a periodic structure. You move parameters, the eigenvalues decompose, then you move a little bit, then again decompose it, and the six happens independently.
But it's like an open part in the
that's it. Yeah, I do nothing else.
Yeah, but my question is, does it have meaning to go to the boundary of the module?
I don't think so. No, I think it's just perfect by itself.
No, it's already interesting, but okay. All right, thank you.
If I could ask a question, the star product, can we think of it as a deformation of the wedge product?
Yes, of course. Yeah, in classical limit, which is not point of a manifold, because you go to t equal to 0, which I remove, you get the usual cup product on command. Yeah.
Is there some easy way to understand the semi-classical limit, just the first order deformation?
No, it will be just kind of you add kind of maybe curves of the smallest possible degree. That's it.
Right. But so if I understand correctly, this is kind of the wrong way of looking at it. You should really be deforming as a Frobenius manifold. Is that correct?
It's no Frobenius. It's you see that the composition of derived categories, I think it works for this larger class of non-compact varieties as well. When you don't have perfect pairing, you have maybe degenerate co-pairing, but no perfect pairing at all.
Okay, so you can still define the Gromov-Witten invariance and
yes, yeah. I said it orally. If you can make Gromov-Witten invariance not as a potential, but the connection or quantum multiplication can be defined in a non-compact situation as well.
I see. So there's no direct. It just feels like this meromorphic connection is related only in a very roundabout way to the Gromov-Witten invariance. I mean.
Yes, yeah, but yes. It's roundabout, yeah, but still, I don't know what to say about it. Yeah.
Okay. Any other questions for the speaker?
Yeah, maybe I'll just want to add some kind of fantasy about what should go on. When you get a semi-orthogonal decomposition of your category of coherent shifts on your variety, let's say smooth projective variety, it should be given by certain, you can make something like projector to each term of semi-orthogonal decomposition. It will be end of functor. In the center functor should be given by some kernel. So it will be complex of vector bundles or perfect complex of the square of your variety. So it means that if you choose this Gabrielov path and so on, we should produce these remarkable kernels, which are complexes of vector fields on the square of variety. And where to get it? It's something like correspondence, something on the square of variety. And my guess is because we count this, we have this quantum multiplication by operator, this k by something. At the end of the day, we count something like this operator in terms of Gromov-Hitton theory will be given by combination of classes of some rational curves with two mark points, input and result of my operation. So you get some kind of object, maybe in K0 and square of a variety, but you get infinitely many of them because you get arbitrary degrees, and when I get deformation, I get really infinite sums. So in some mysterious way, it should be transformed to some finite expression, and then it will be projector. Okay, so maybe that's all what I can say.
Okay, any other questions for the speaker? So if not, let's thank Maxim again.
Okay, and I will send you slightly corrected later. Okay.
Great, and the lecture notes will be posted on the website and the video as well, and soon we'll have YouTube versions of the videos.
Okay.
Okay, so see everybody tomorrow at the same time.